So in last video we were discussing about the separation of lanthanide ions by ion exchange method, and as you know that during the separation of lanthanide ions by ion exchange method, complexing agent plays very important role. And complexing agent, it increases the capacity of an ion exchanger resin to fractionate the lanthanide bands into individual bands, and therefore plays important role in the individual separation of lanthanide ions. And meaning of this is complexing agent increases the capacity of ion exchanger resin and favors the better separation of lanthanide ions. The extent of separation depends upon the separation factor. It is denoted by alpha, and when the separation factor is equal to 1, separation is very difficult or not possible. And when the separation factor 1 deviates from unity, that is its value, if it is less than 1 or greater than 1, then separation is possible. So greater the deviation from alpha from unity, greater is the separation. Now consider the equilibrium reaction for the exchange of lanthanide ions with proton of the cation exchanger resin. So when lanthanide solution it is added in or poured in the ion exchanger resin, that is cation exchanger resin, then lanthanum plus 3 ions are exchanged with cations, that is H plus ions, and these are adsorbed on the surface of cation exchanger resin in the form of Ln R3 plus protons set free in the solution. The distribution coefficient, that is lambda 0, for one lanthanide ion between resin and aqueous phase is, actually lanthanide ions now they will exist as a adsorbed lanthanide ions on the surface of resin, as well as some lanthanide ions exist in the solution, but this or aqueous phase, but these are in contact with resin. And the distribution coefficient lambda 0 for this is, lambda 0 is equal to concentration of lanthanum plus 3 ions in resin, that is adsorbed lanthanum ions, upon concentration of lanthanide ions in aqueous phase. So this is equal to concentration of lanthanum plus 3 solid. Actually when it is adsorbed on the surface of resin, that lanthanum ion it is considered as a solid, upon concentration of lanthanide plus 3 ions in aqueous phase. And this is equal to, actually for simplicity we are ignoring the positive charges, and therefore concentration of lanthanide in solid upon concentration of lanthanum in aqueous. Here concentration term is missing here. So concentration of lanthanum in solid upon concentration of lanthanum in aqueous. Similarly for other lanthanum ions, actually in solution there is a mixture of lanthanide ions. So for next lanthanum ion, the lambda 0 dash, that is the distribution coefficient, it will be concentration of lanthanum prime solid upon concentration of lanthanum dash or prime aqueous. But the separation factor alpha, it is the ratio of distribution coefficient of two ions, that is lambda 0 dash upon lambda 0. Accordingly we know the value of lambda 0, this is the lambda 0 and this is lambda 0 dash, and we get concentration of Ln dash solid into concentration of Ln aqueous upon concentration of Ln dash aqueous into concentration of Ln solid, and this is nearly equal to 1. And if alpha is equal to 1, then separation becomes very difficult, and therefore there is a need of complexing agent. So in presence of excess of complexing agent, that is AA, that is bidentate ligand, separating factor alpha deviates from unity and lanthanide separation becomes easier. Now when excess of complexing agent is mixed with eluent, the equilibrium established, it is given by this chemical equilibrium, that is lanthanide ion +3 in aqueous phase. When comes in contact with complexing agent in aqueous phase, n moles of complexing agent, then there is a formation of, actually this lanthanide ions form the complex with this complexing agent and we get ln AAN aqueous. So for simplicity again charges are neglected, and for this chemical equilibrium state, according to law of mass action or stability constant, it is given by K ln, stability constant of this complex lanthanide ion, that is K ln AN. This is equal to concentration of this complexing agent. So stability constant for this ion K ln A, it is equal to concentration of ln AN, this is the product, upon concentration of ln aqueous into concentration of this complexing agent raised to n, because there are n moles of complexing agent, and by rearranging this equation we get concentration of ln AAN, that is the concentration of complexed lanthanide ion, it is equal to stability constant of ln AN into concentration of lanthanide ion in aqueous into concentration of complexing agent. So this is equation number 1. But the total concentration of lanthanide ion in aqueous solution, it is the sum of concentration of complex lanthanide ions and non-complex or uncomplexed lanthanide ions. Actually in solution both the lanthanide ions are exist. Some lanthanide ions they form the complex, whereas some lanthanide ions they are not forming complex with chelating agent or complexing agent, and therefore distribution coefficient for all the lanthanide ions, it is equal to lambda is equal to concentration of ln solid, concentration of lanthanide ions in solid phase upon concentration of lanthanide ion in aqueous phase. But in aqueous phase lanthanide ions are uncomplexed as well as complexed with chelating agent, and therefore upon C ln aqueous into C ln AA, this is the concentration of complexed lanthanide ions and this is uncomplexed lanthanide ions. And from equation 1 and 2 we can write lambda is equal to ln or concentration of lanthanide ion in solid upon concentration of lanthanide ion in aqueous. Just we are substituting the value of this concentration of ln AN, and this is the value of concentration of ln AN. So K ln AN into concentration of A aqueous into concentration of lanthanide in aqueous solution, and therefore after simplification we get lambda is equal to concentration of ln solid. Now here concentration of ln aqueous, it is a common term, into K ln AN into concentration of A aqueous raised to n. But we know that lambda is equal to concentration of lanthanide ion in solid upon concentration of lanthanide ion in aqueous, and therefore lambda is equal to lambda 0 upon 1 plus K ln AN into concentration of A aqueous raised to n. Now in excess of if excess of complexing agent is used, the stability constant of complex is very high, then the equation can be simplified as lambda is equal to lambda 0 upon k ln an into concentration of A aqueous. And this step shows the influence of complex ion on the distribution of lanthanide ions between the solid, resin and aqueous solution. Now for other lanthanide ion, that is Ln dash, we can write distribution coefficient as lambda dash, it is equal to lambda 0 dash upon k ln dash A n into concentration of A aqueous raised to n, and the separation factor alpha, it is the ratio of lambda dash upon lambda. Now we know the value of lambda dash, we know the value of lambda, and therefore by substituting the value of lambda dash and lambda, we can write, so the common terms gets cancelled here. Concentration of complexing agent in aqueous raised to n, these two terms are similar because concentration of complexing agent is same. These two terms will be cancelled, but lambda 0 dash and lambda 0, these will not be cancelled. These are the different terms. Even stability constant of lanthanide ion in complex lanthanide ion, it is different for different ions, and therefore these two terms are also not cancelled, and therefore alpha is equal to lambda 0 dash into k ln A n, this is the stability constant of one lanthanide ion, upon lambda 0, distribution coefficient of one lanthanide ion, into ln or stability constant of ln dash A n, this is the stability constant of other lanthanide ion. So here important thing is the separation factor alpha, it depends upon stability constant of the complex lanthanide ions, and this stability constant is different for different lanthanide ions because the stability of complex lanthanide ion, it depends upon the size of lanthanide ion, and because of lanthanide contraction, size decreases from lanthanum plus 3 to lutetium plus 3, and therefore stability constants are different, and greater the difference in stability constant, greater is the deviation of alpha from the unity, and therefore we can say from this actually expression, it is clear that the extent of separation of Ln plus 3 ions depends mainly on the stability constants of their complexes. Hence, if a chelating agent with lanthanide ion forms chelates of different stabilities, then separation factor will differ significantly from the unity, and the separation of individual lanthanide ions can take place. And meaning of this is the complexing agent plays very important role in the individual separation of lanthanides. So greater the difference between stability constant, greater is the or easier will be the separation of lanthanide ions. So in this way, here the role of complexing agent is proved in the separation of lanthanide ions. Complexing agent plays very important role in the separation of lanthanide ion. Meaning is when separation is carried out without complexing agent, it will be very difficult, whereas when complexing agent is used like EDTA, citric acid, then separation will be easier.